Today's lecture 4 continues on the discussion of linear viscoelasticity based on the book of Nonlinear Polymer Rheology published by Wiley.
All right. Any questions? So we are still in the mode of introduction. I like to think all this part as introduction before we hit the real content of it. So before that, let me make up by showing you what viscoelasticity is. So this is the PDMS I mentioned last time. I keep forgetting to bring it to you. It's uncross-linked. It has a molecular weight. It probably has a molecular weight of around 500,000. And it is uncross-linked, but you can see it bounces. So it's clearly elastic, even though it's not cross-linked. So this is a first impression you may gain in terms of what is viscoelasticity. If you leave it for a while, under gravity will start to flow, given enough time. So the contact time, if you like to guess about the tau in this PDMS, is just very short compared to, let's say, because my contact time to the table is a fraction of a second. So if your internal time is much shorter than a fraction, much longer than a fraction of a second, that molecule cannot move. And that's why this PDMS look like a rubber ball. So a lot of what we will learn in this course will be very useful for us as a polymer scientist who eventually move on to learn why my polymer is brittle or ductile. For example, this polystyrene fork is obviously rather brittle. And I have my earphone broken because they didn't use the right material to have enough ductility. So this is the other side of polymer science. It turns out to understand any of that, our course is essential. Our course in the way we discuss it, not in the traditional way that you have learned previously in rheology. Okay, so let me continue under introduction. We had several topics if you go back to your notes. So today I will describe a little bit about rheometry. In other words, we had definitions about how I guess the best way is to describe Maxwell model, which is a very simplified way to say something about viscoelastic material. Maxwell actually predicted, for example, if I know there's, I mean, this is not something I had any plan to do. Basically, one of the, perhaps I should not omit too much, one of the way to learn about viscoelasticity is about identifying the relaxation time. And then the way to identify it, typically, one of the good way was to do so-called oscillatory shear. So you basically move your upper plate back and forth, and you observe what the stress response is. From the stress response, you will be able to tell there's something that's characterized the elastic response determined by G prime, and there is something characterized the viscous response characterized by G double prime. I'm sorry, this is this was not what I had to plan to do. I hope. So G prime, G double prime. I assume several of you do not know, correct? Of course, it's all in the book, but I just want to. I want to figure out what would be the easiest way. I know I don't want to. I mean, much of this discussion on linear viscoelasticity is not as essential as describing the rest of the nonlinear response. But I always hesitant not to be self-contained enough. Look like I'm a little bit stuck here. If I can be brief, but this of course could mean that that you don't have a very thorough digestion immediately. But basically, if you examine your material in this oscillatory way, so really I should speak about dynamic shear here. I just in my mind took for granted that you all know this, and all of a sudden I realized that I'm not able to proceed with this very well without mentioning this. So basically, you have shear. You move your plate up and down, back and forth, and you find if it's linear response, which means small amplitude, which means gamma 0 is small, then you find the stress response will also be a sine function. But they are not going to be in phase with the strain, and there will be a delay angle. And the simplest way to realize is this function can be expanded into a cosine and sine function, and therefore you will be able to write this as something of this form. Okay? And this, I flip it because I want to see where in my book I wrote this down in detail. Somehow I don't seem to find it properly, which is very, okay, here it is. Yeah. Which is impossible. So this is equation 111. So you can see how it was done. So basically, we claim that if your material is viscoelastic, then it turns out its response will have a Newtonian-like viscous term, and they will also have a Hooking-like term, elastic term. Get it, right? So universally, this is not just for polymer, for anything. And so far, my discussion on this side says nothing about model. All the concept you need to know is I have introduced the idea of linear response in the sense if I have a strain, it turns out I cannot apply strain for free, meaning in order to apply this deformation, I must exert enough stress that goes with it. In other words, when I produce deformation, my material will resist this deformation in the form of giving me a resisting force, which is stress. And we're saying they are linearly related. So this expression here is independent of any model. But because it's, I introduced G prime and eta prime very arbitrarily because because I can split this into two terms, and I recognize one of the term is proportional to gamma, another term proportional to gamma dot, and the coefficient in front of it is necessarily the quantities of modulus for gamma and quantities of viscosity for gamma dot, necessarily. I don't know more, I just call them G prime and eta prime, because I know G was used to describe modulus, and eta was used to describe. It turns out these two quantities varies depending on the frequency you're using. Okay? That's it. We have no idea so far of what G prime look like, how it would depend on omega, how eta prime would depend on omega. We have no idea. We just know maybe this should be the way it is. So these are just definitions, very, very fundamental, therefore. It turns out the Maxwell model that I mentioned here speaks something explicit about what G prime should be. Okay, so this is, of course, Maxwell model I already showed you is something starting on page 8 and 9. Starting on. And Maxwell model has a specific thing to say about what is G prime, and it is G omega 1 plus omega tau squared. And on the top, it should be just this quantity. So this is I'm trying to again find the Maxwell model's definition for you. It's on this equation 127 is on G prime, and in the limit of small omega, it goes as omega tau squared. So in the limit of omega tau smaller than 1. So this is, of course, is a whole set of discussion that merely shows you that Maxwell model can tell you what is G prime look like. And eta prime is nothing but so-called G double prime over omega. And which is the same as saying what is eta prime, and therefore it also says what is G double prime, which is equation 127b, and this is 127a. So quickly, I get to the end of the story for you that Maxwell model gave you a nice way to think about what G prime is and G double prime is. This is the Maxwell's prediction of G prime, G double prime. And in particular, it tells you when the G prime, G double prime are equal, this crossover frequency is 1 over tau. So this is this is, of course, enough for us, but I really condensed all this in such a short time, in 10 minutes. The useful thing to know is such an oscillatory shear is such an important part of rheological investigation. The rheology as tools, this is the tool part. You do oscillatory shear, you learn about your internal time scale through such a measurement, right? So this is a part that I have not emphasized, I will not emphasize too much in our course because we go to the science part of the rheology, not the tool part. But the tool part, of course, is very important. If anything, this is the tool. The rheology, anybody goes to a rheology lab, typically, if they are not studying the science of rheology, it's to use this to characterize, and one of the most crucial characterization is to learn about the internal time scale, the internal relaxation times. For example, this PDMS, now you see it's no longer, it's getting flat now. I can force it to change shape because it's not cross-linked. And force it to change shape any way I want, including I do it very fast and break it too. We will describe all this in much more details in the future. So this piece of PDMS, you can put it in this, between these two parallel plates and make a measurement. It turns out the way you find out how this, phase angle changes. Turns out this phase angle is such that the tangent delta is G double prime over G prime. And according to Maxwell model, that is nothing but 1 over omega tau. And of course, the rest is something I hope you can quickly recognize, that there are two limits when omega tau is much larger than 1, okay? Then of course, tangent delta is 0, yeah? Tangent delta is 0 or delta is 0. If delta is 0, then of course your stress is in phase with your strain. And conversely, when omega tau is much smaller than 1, tangent delta diverges, and that's because half pi of tangent delta is divergent. And when this is half pi, when gamma delta is half pi, the sine turns into cosine. And what is cosine? Well, the gamma dot is cosine, which means your stress now all of a sudden is proportional to the shear rate, like the Newtonian law tells you. So all of a sudden your response turns into a liquid-like response instead of solid-like response. Because when sigma is in phase with gamma, that's the solid response. That's delta equals 0. So you got a solid response for that limit and liquid response for that limit. So within this very short thing that I really was not prepared to describe today, we covered everything we need to know about a essential part of, or foundational part of how you make investigations, because you need to know tau, for example. We have spoken quite a bit last time. I even give you the insight about tau for untangled polymer being proportional to the molecular weight to 3.4 power or 3 power. And now we completed that discussion in terms of at least experimentally how I determine that. Right? Any questions? So I don't mind being a little bit fast here, because at least if there's anything you didn't get it, we have the recording. You can go back and review it again. So, but this is yes, please. Yeah. Yeah. Well, omega tau is much smaller than 1. It just means you're oscillating very slowly. Okay, right? In that limit, tangent delta become infinity, right? Tangent delta infinity is delta equals half pi. What is the state? Oh, that's a very trivial point. It turns out I usually, last time I do it with my saliva. It turns out you can put your saliva, my finger can hold water between my finger because of surface tension. And so you have no trouble bringing your sample in between a small gap, and the surface tension will hold it there. Nothing will flow out. Yeah. So no. Okay, so you're jumping a little bit, one step ahead. So DMA is a device. I was about to talk about rheometry. We'll talk about it a little bit. DMA typically is a device where you do stretching, like this. And obviously, I cannot do very well to hold a piece of water that way. So for your material that is water-like, you have to use this mode, shear. Learn the same information. If it's a piece of solid-like material that you have enough integrity, then you can hold it and do DMA. That's the point. Yeah, no, in fact, that you're missing half of the knowledge. If you know about DMA, give you viscoelasticity, that's when you have a solid-like material. But for anything else, you go to this mode, the shear mode. Yeah. Okay. So we're now back to rheometry. And we only say a few things that are necessary. So we can talk about a little bit about capillary rheometer. In the middle, I will explain everything about the different features. So the capillary rheometer is highly useful. People use it a lot because it is a way to mimic polymer processing. Okay, and I suppose in today's climate, this is particularly versatile or relevant or pretend, very, very relevant geometry, because there are folks of you who do 3D printing. That all is like coming out of a little nozzle. Where you may just envision that when you see capillary, it's a little tube. And your material is loaded here, and there is a piston that pushes it down. You can push it down with a certain velocity, or you can push it down with certain pressure, depending on the design of your rheometer. Okay? So since a great deal of polymer processing involves this type of extrusion, like many injection molding, blow molding, many things involve this type of geometry. Film blowing. So this is, of course, one would like to know on lab scale how my polymer behaves in some sense. And so I will just pick up a case where we call this die, where this die is cylindrical. Of course, this die could also come out like with a cross section like a rectangular shape. But we'll just concentrate on discussing a simple case where this cross section is circular, right? It's a circular die. Material comes out. And the basic characteristics of this is this die has a diameter and has certain length, L. And the rest is somewhat technical. This die may come at an angle, okay, or not. So in that case, I should describe everything is above this. So there are cases for certain purpose, we want this die to be to have an entry angle like this, and the material is going to be squeezed into this die from that entry point. There are quite a few, several elementary pieces of information. First thing first, because it's a cylindrical die, your description can adopt so-called cylindrical coordinate, where obviously the variable is the radius. So it turns out, really depend on your perception about it. It turns out as I squeeze my material through the die, I'm mostly creating shear. Shear has a, Jesus. Shear has a very peculiar feature, as you have already appreciated. We tried our best to show shear in this manner. It basically has I hate to invoke any fancy word called velocity gradient, but basically you have a gradient, right? If you look at your velocity, here is 0, here is finite, and anywhere here is in between. You have a gradient. That gradient is perpendicular to the moving direction, to the shearing direction, right? The gradient is in the y direction, the moving is in the x direction, and the third direction is vorticity direction, so-called. So that's the feature of shear. It turns out in fact, this is the subject I should mention right away. It turns out not only when we discussed this, last time lovely it came out, that we have had the assumption that the shear is homogeneous, right? The velocity is linearly increasing from bottom to top. But there was actually one additional assumption we made. Yes. So that one is quite commonly discussed. That there is no slip, which means at the bottom, if my bottom surface doesn't move, then my polymer on that bottom surface, next to that surface, is also not moving. So it's called no slip boundary condition. So that's common. But what is not clear is how do you know there's no slip boundary condition applies? That's the question. How do you know? In other words, this is discussed under the assumption that there's no slip. So under the no slip condition, when you think about extrusion through a die, necessarily it means whatever material that's coming through this die, you take a free ride, you're coming out, as this piece of, we call it extrudate, right? As this piece of material comes out, the material near the wall will attain 0 speed because the wall is the surface that doesn't have any velocity. Get it, right? So think about what comes out like an onion. That most outer onion that's next to the surface of the die will not have any speed. It turns out the middle has maximum speed. So if I draw this die like this, I don't know how many of you have this notion before, but that's what it is. The maximum speed is in the middle, and it will come out with more or less like a parabolic shape. The water from your fossil, it's all like that in principle. Okay. If you take a way to see how the water flows in your pipe, it all does this. Because there, I know it does this because we know for water, there no slip boundary condition holds rigorously. Okay. I just want to quickly get you a sense of how materials comes out. It turns out that the details are related to the following. You see, you can already start to appreciate. The appreciation that you need to have is this, right? I don't think we are wasting time here by realizing this capillary is like two pieces of shear, right? Remember, this is a shear. It's like I have two pieces of it, right? As if the middle plane, there's a middle plane that's moving. I know, just in as, are you following me? Meaning, all I'm trying to say is that there is a velocity gradient, just like we had it in a simple case of shear. That the velocity changes its speed across a gap. And here, that gap is my radius of the die. My speed is 0 here, maximum there, and changing all over the place. So there is some velocity gradient. I know we have not tried to do anything fancy in the past. I showed you that V over H is the shear rate. But if you want to get even just slightly fancy here, what you have is really, what you have is really, if you allow me to use calculus, is really this. You have a velocity that's going to the x direction. It's changing with y. And since it's a simple shear, in other words, there are no other velocity component, I don't even need partial derivative. I can just use the total derivative. No, I don't mean that. I just want you to think that there is a velocity gradient. Right? Don't think too much. Meaning, obviously, simple shear is simple shear. Capillary is capillary. Right? I just want you to draw some analogy, some appreciation of where things are coming from. But you all appreciate, Hobi, this is as little or as much I'm asking you about calculus, that the changing of velocity over space, when I describe it, we call that velocity gradient. And that velocity gradient for simple shear is a constant. Yeah? And that constant is this, provided you have homogeneous shear, right? That was what we covered last week. So all I'm trying to invite you to think about is that for this capillary, you also ought to think about a velocity gradient. Since velocity gradient implies stress, according to Newton, I necessarily want to introduce the concept of shear stress in a capillary flow case. And the two direction that's important to describe is in cylindrical geometry is simply the z direction and r direction, right? So the rest is the same. It turns out the fact you have you have shear, it means that the force is acting on a surface whose normal is perpendicular to the force direction. So same here. So you can imagine the force, it will be in z direction, and it's acting on every layer of the onion, and that's my r direction. So if I look into the die, I have this r coordinate here, and z then is going into my screen. So in any case, it's quite straightforward for me to say that you can visualize a shear stress in capillary by, if I'm allowed to remind myself of the notation, it involves the shear stress occurs because the deformation has a velocity gradient in the r direction, and the shape change is in the z direction. And this stress, shear stress, without going through the solution of the equations, it turns out it is related to the pressure. So see, when I said there is a pressure, it means there is a pressure at the beginning of the die. And there's a pressure that's coming out of the die, which is negligible atmospheric pressure. So this is a pressure gradient. And what I was trying to say is it turns out the stress at any r is proportional to r. This is the part I don't plan to convince you, rather through this result to you, that no matter what is your material, I can of course try to find the equations in the book. No matter what is your material, when they are being forced to come out of the die, okay? This is the equation 3.7a. When they come out of the die, it will, as you describe, see, I try to describe, as you try to describe your sheared surface, like this surface that I depicted here, is each of that surface is a cylinder, co-center cylinder. There are many cylinders of different diameters, okay? And at a cylinder of radius of r, I can tell you the stress will be proportional to r. Well, this goes all the way, valid all the way to the center. R equals 0. Okay? R equals 0, according to this formula, says the stress is 0. And the reason the stress is 0, look at this lovely thing that I draw here. The reason stress is 0, remember this is the velocity field. You realize this velocity field has a maximum at the center, which means its gradient at the center is 0. There's no shear rate at the very middle line. Okay? So I'm just connecting the dots here for you that it turns out your stress is maximum at the wall of this die. Okay? True for any material you attempt to squeeze out. True even when you have slip, which is a big subject. That's the formal part of the nonlinear rheology on chapter 6 that we're going to eventually get to there. So this is universally true. the rest becomes unclear. In other words, if you give me a piece of material, I extrude it out, I won't be able to tell you exactly how that velocity field will look like. Okay? I will not be able to tell you how this velocity field look like. Unable. Unless you tell me that, oh, you already know the relationship between the stress and the shear rate. If you do, then I can plug this in and start to integrate and solve it. Otherwise, you have no, a priori, you do not have any way of knowing what is the velocity field. So today, since we do a lot of visualization, we can say, oh, let me go measure the velocity field. And then infer about what's happening. That is an approach that has not been taken by anyone. In general, we admit that this velocity field is unknown. It's unknown if your constitutive relationship is unknown. If you don't know this equation, if this relationship is unknown, then the velocity field is unknown. I'm making a quite important statement. It becomes catch-22. In other words, it means that capillary cannot be a good way to study constitutive relationship, because you started with unknown, so how can you get to the part you need to know? In contrast, you see, this is where traditional rheology is about, the essence, where we can appreciate the essence of traditional rheology, and also where, alarmingly, where it breaks down. Think about here. Think about our dear simple shear here. Here, we pray to God, no matter what viscoelastic material you gave me, I actually already know the velocity field. Well, by assumption, though. By convenience, by necessity. So for anyone, like Alex and Daryl, that you know about rheology before, this is how we can make progress. We assume we know the velocity field. If we don't, we'll be in the same darkness as the capillary, where we don't use it to determine anything because we wouldn't know how to compute. Okay. Any questions on this point? So, so that's the sort of the only message I'm going to try to convey to you. And then it turns out, luckily, for what we need to talk about, we actually don't need to worry too much. We only need to speak about a case like water coming out of your pipe. In other words, yeah, you say you don't know the flow field, the velocity field. What about in the case that you actually necessarily do know? That is the case of where you know your material is Newtonian. When we say our material is Newtonian, it just means that we know that this is true. Right? I'm just nothing but this is nothing but the shear rate. And my velocity is just a function of r. So indeed, I want to say this from upfront. Typically, textbooks don't even normally, very often don't have to bother. In other words, when we talk about capillary rheometry, we typically do not discuss about the fact this dye is of a finite length. It's not infinite. Only in the limit that we ignore what's happening at the end and what's happening at the entry. Only in that limit, I can speak about the fact your velocity is only a function of r. In that case, a total derivative is good enough. We don't need partial derivative. So plug this into PL equals half R. You can solve for it. Even you can solve it. Integration of x is x squared. That's why I say you solve it. So this differential equation you can integrate on both sides. dv equals dr or whatever function, and you integrate. So it turns out you integrate and you get the results. Equation, there are so many forms to it. Equation 3.9 is the result. Basically, you find, as I try to show you, that your r is indeed a function of, your velocity flowing down is indeed a function of r, and it has its maximum at the center and 0 at the wall. And this expression will satisfy that. And the rest is all quite trivial. So in any case, in the case of Newtonian, indeed, your velocity field will be parabolic that look like this. The maximum velocity, of course, is related to I always wanted to do it in a way that's little bit physically meaningful. Let me try. Let me try by doing this. Looking at this expression, you can see what is so-called the wall stress. The stress at the wall, that's maximum. That's when R is R. And sometimes we like to call this 2R equals D. So it's really PD L D4. Okay? That's the wall stress. Okay? So in terms of that wall stress, there got to be, for Newtonian, right? Got to be viscosity and shear rate at the wall. How about that? Yeah, should be. Because that Newtonian law should apply everywhere for every layer of that onion layers. So I just want to reduce this maximum velocity in this notations that are defined here. So I noticed in my equation 3.11, I have the maximum velocity expressed as P16L D and So let me try to reduce this because this is uh, uh, this is 4 times 4, so that this is the wall stress times d over 4 divided by shear rate, shear viscosity. So I deduced, if you, I know if you can follow me quickly enough or not, I deduced that, let me just redo it. So if I move max d over 4 to this side I have sigma w over eta. And that's nothing but shear rate at the wall, right? Yeah? So all I tried to do for you of this equation, I no longer need it there, of this equation about the expression of maximum velocity, it turns out that maximum velocity can be written as wall shear rate times d over 4. In any case, all this is elementary to manipulate. The bottom line is that you got a top velocity at the middle, and that top velocity is related to the wall shear rate in this way. And the wall shear rate, of course, depend on the property of your material. In other words, it depends on the viscosity and the stress. Okay, so this is the first part of the capillary rheometry. The other part that is related to this, all this notation, is how fast it comes out, right? Because you got this material that tries to come out. Gosh. You got this material that's trying to come out. Okay, try to come out. And it come out at a certain rate. In particular, it comes out at a rate called Q, which is how much material comes out per unit time. Okay, I use the word Q here. How much volume of material comes out per unit time? It turns out that's a very measurable quantity. In fact, the way we have a rheometer that one day we can go our lab and see it if you need. But basically, it's like every given moment, how much material is coming out that has a certain density. So if you weigh your material with the density known, you know how much material per unit volume is coming out. And that's a accessible quantity that we need to use all the time. And that quantity, and that quantity is what written in the book as equation 312a. Basically, it's just you just integrate because you just have each layer. That's 2 pi r. That's the circumference. The thickness is dr, and the material coming out is v at that r. So that's a elemental part of the material coming out that you integrate. You get the final result. Very easy. And then you get this is the final result I need you to remember. So there are two results. One is that, the other one is the relationship between stress and the pressure gradient. So pressure gradient is accessible, and the rate coming out is also accessible. It has the right unit. It's volume per unit time, because shear rate has the dimension of reciprocal time. So this is something we will use multiple times in the near future when we discuss the real part of the polymer rheology, the physics part of the nonlinear polymer rheology. But this Newtonian aspect is very useful. It gives you a sense of what to expect, how fast it comes out. At least for Newtonian limit is related to, of course, right? This is nothing. This is nothing but viscosity, and you can, of course, plug this in. You will know exactly how Q will depend on the pressure gradient and the diameter and the viscosity of your material. Predictably, meaning because you know your. So for Newtonian material, this capillary can be a way to measure viscosity, for example. That's what I'm trying to say. Because you know, as soon as you determine your Q, knowing your pressure, this eta is given in terms of those two quantities, just like Newtonian law should. Okay, so this is the part that I wish to go through. Any questions? I speak about this part because it turns out in the future we will have an opportunity to come back to it and realizing our dear 100 billion pounds of polymer processed every year, half of that subjected to this geometry, is not Newtonian fluid. What happens? How happy are they going through? And what could happen when they try to enter? Moreover, what happens, speaking of no slip boundary condition, what happens to the extrudate? Do they necessarily come out smoothly? And if they are not smooth, what's the origin? Because if it's not coming out smoothly, then anything you manage try to do, injection molding or blow molding, may be ruined by it. So there are millions of dollars spent all the time trying to deal with the challenges in extrusion, because our polymer is not an innocent Newtonian liquid that would come out smoothly and obey this particularly simple law. Not at all. So I think if you have a moment, what should come out to you very, very quickly. Right associated with that equation is something is this. You know your polymer will have a relaxation time. Tau. I just even spoke about you go to your lab and do this, and you may get a relaxation time. And you have got this relaxation time now. What are you going to do in connection with what I just spoke about? Well, you're going to be able to evaluate, as I claim to be true, that we want to produce 1,000 bottles in an hour, not 5 bottles in an hour. Which means this thing coming out through the die very fast. According to what? According to this formula, it tells you how fast it is. Yeah? If you know the Q, you want the Q to be as large as possible, which means your shear rate at the wall will be as fast as large as possible. Then you can construct what? How do you indicate that what's coming out is fast or not? Let's see if it's in, I don't know where we have it in tool. Let's see, so have we not talked about that? Meaning, this is just a matter of switching to different discussions, but the story is the same. What we need. Weissenberg number, yes. It's as boring. So we talked about, let's recall, I took very slow pace telling you the meaning of Weissenberg number, or the meaning of the ratio. Weissenberg number essentially involving a ratio. The meaning of what if moving one h to the right takes negligible amount of time compared to tau. In other words, within tau, I can move 1,000 h to the right. That's Weissenberg number equals 1,000. And I indicated that is the limit. Your polymer is really suffering, meaning it has no way to diffuse. It's subjected to this affine deformation, which at some point may break down, and how it will break down was the whole core question in nonlinear rheology that has no proper answer for a long while. So we learned all this in simple shear. Does it really matter when we have capillary? It's still this. Remember, I just told you that this capillary is dominantly a matter of forcing your material to undergo shear deformation. And admittedly, the last thing, if there is anything I omitted, is that you will find in this capillary the velocity gradient, or the shear rate, if you like, is a function of r, and since it's quadratic, therefore it's linear in r. The reason it's linear in r is because it's Newtonian, therefore shear rate should be proportional to the stress, right? And the stress, I just told you the formula is proportional to r. Of course, everything is what I said, right? Meaning, your shear rate is not identical anywhere in capillary, unlike the simpler case of simple shear. Nevertheless, the concept of shear is the same. Moreover, I can speak about shear rate anywhere I want, including near the wall. There, the whole notion of what is shear comes back to me, that I should think about. This Weissenberg number, well, you may say, oh, that's Weissenberg number at the wall, right? Fine. Fine. This number, what if this is much larger than 1? Well, the poor polymer will have the same issue. When I say the poor polymer, I should just have this copied to the tool. Let's see. I should just have this thing constantly be part of our. Cannot believe this PC is this slow. we should just keep. I remember showing you this, right, guys? So you should just remember, keep copying this image everywhere, anytime, all the time. So this is our thing. And try to diffuse around, but in this limit, there's no chance. And this thing is just suffering tremendous shape change. Remember the shape change? Just give you a prelude of this. The sample was initially in this big reservoir, and you're trying to squeeze this thing into a little hole. Okay? Very unhappy, the guy is, the polymer. And the question is, what do they do? How do they respond? And we talked about affine deformation before. Did we talk about affine deformation? I think we talked quite a bit about that affine deformation, right? I try to it's here. It's here we discussed it. So obviously, no matter what you do, the polymer was unable to move because of what we said about reptation. That the tau is such a strong function of molecular weight. It tends to have a big tau. So polymer is unable to move because they live in a tube. And then, since they are constrained by uncrossability, we may initially even treat them as if they are affinely deformed, meaning you microscopically shear it 100%. The chain also sheared 100%. Well, when your WI, let's say, is 100, it means 100%, right? That's 10,000. The question, so this is where we can switch back from percent to I hope everyone is familiar with this, right? A unit of 1 is, of course, 100%. That's what we say. So shear 1 h to the right, that's 100%, we call it. But it's a strand of 1. This is saying within tau, you can have a strand of 100, right? Because it's 100 h to the right. Can a polymer at the chain level also being sheared 100, undergo 100 strand? If it does, then you say, oh, they are being affinely deformed. But it's next to impossible to imagine that the polymer somehow does not escape. I think I'm using a negative statement to say something. It's hard to imagine, double negative again, right? It's hard to imagine that the polymer does not escape from this constraint and happily go 100 strands to as externally doing it, microscopically doing it. So that is exactly all the question. Oh God, where did I lose my? That's exactly all the question there is when you no longer have affine deformation. So the quiz I gave you was as soon as I introduced you this, speaking about how fast we're squeezing a piece of material out, where you learned about a way to think about how fast it's being sheared, you automatically will recall the problem we are confronting, the problem of what happens at high Weisman. I have a couple minutes. I want to use this couple minutes in a crucial way. I may even save you some time since I opened this slide, since I have the slides here. I may even go ahead and start to use the slides for you. It's easier. Oh, I can never understand why it refused to let me go down. Okay. So here's the slides I want to go through with the 5 minutes left. It's essential. It's ABC of rheology. It's ABC of polymer rheology. It's the most elementary part of what is often not discussed sufficiently. So I'm just drawing you better than my handwriting. Consider simple shear again, right? Consider so-called startup, which is, I think I introduced that concept, right? Just all of a sudden you started. I draw all there is. At t equals 0, you start to move upper surface. Your sample start to change its shape by definition in a shear manner. Your degree of deformation start to increase linearly with time. Your how fast you're doing it is precisely determined by you as an experimentalist, knowing what is V, what is H, so the shear rate is there. And so every shear rate is just the amount of strength you are imposing per unit time, right? So as your time accumulates, you're increasing the strength. For this, I'm only discussing the case where homogeneous shear is valid. However, there's something extraordinarily important to understand and appreciate. First is when you put this material in there, all of a sudden you start to shear. What response do you expect to get? In other words, does your material feel like a piece of solid or feel like a piece of liquid? Initially. And here I have to make a remark that through my experience, there are people who have finished their career in rheology and unable to answer this question correctly. Because I think we spent plenty of time talking about flow being an irrecoverable type of deformation, right? Reaching irrecoverable limit, right? We talked about that a great deal, yeah? This PDMS, for example, just give you an example, is I have to pretty fast trying to smash this ball onto the table. It's a fraction of a second. So in that limit, it's elastic, okay? It's fairly elastic. However, the tau of this polymer is only a second or so, okay? Pretty fast, okay? Fast to what sense? In the sense, it's hard for me to demonstrate with this PDMS about the recoverable part of deformation. In other words, when I stretch, well, you can see it recovered a little, but hardly any. Yeah? I mean, I do the best I can, a little bit. Which means, yes, for this polymer, because it's so fast, and I was doing 3 seconds, and this thing relaxing 1 second, so quickly I reached the irrecoverable deformation limit, or flow limit. I'm asking you, in a simpler way, does the material flow in the beginning? I see you shake your head. Everyone agree with Alex? Does the material in the beginning flow? And my colleague says, of course it flows. It always flows. And I tell you, I confess to you, if you ask me the same question 20 years ago, I probably will go with you and say, of course it flows. It right away flows. You have motion. Things are moving. You have a velocity even. Plus there's a velocity field, gradient. So I would not be so sure that I have a clear way to answer it. So let's see, as an experimentalist, how do we know it flows or not in the beginning? In other words, the beginning response is liquid-like or solid-like. Well, we can do the experiment. You got a rheometer, one of which could be just shear. You simply shear it and you sense the resistance to this deformation in the form of the force that you need or you sense on the surface. And you find that if this material is really a piece of a liquid responding as if it was flowing, then according to Newton, you should have velocity. You should have a stress right away, instantly, because your shear rate is already established beyond zero, right? It's a finite shear rate, so it should give you a finite stress. Your viscoelastic material, this would be another theorem I can say, will, if you claim your material to be viscoelastic, number one. Number two, if you claim to have good enough time resolution, for example, capturing the stress, the force you can sense on time scales much shorter than your internal relaxation time, tau, if you can do that, then I claim you will never see what I just showed you here. It will always be like this. Well, what this says? This says, oh, if you go to your lab and you find your stress start from zero, then you can go ahead and tell every friend of yours saying, you know what? The stress response is not flow-like. Stress is zero means it's hooking-like. I think I missed the E here. It's hooking-like. And therefore, your response is solid-like. The fact that your stress starts from zero is a proof that your material is responding solid-like. Or, this is the one that I once had this as a footnote in the book, and I decided to take it out, I think. This is the last mystery there is, that our polymer, by definition, when you start to shear, will, of course, by definition, attain a shear rate, yeah? By definition. And therefore, by definition, if any part of my material is viscous, by Newton's law, it should give me a stress. The mystery I have not solved with this book, with much of what we discovered, is why the stress is so negligibly small. It drives me completely nuts. Why my material, my dear polymer, is unable to produce a viscous stress for me, measurably large. So this isn't that such a deep question about the following, that this polymer, as you know, this polymer obviously has a viscosity much higher than honey, much, much, much higher than water, right? Yeah, very high viscosity, this material, yeah? Yet, it does not produce any stress for me at the beginning. I confessed I don't know the answer. This remains maybe for your generation. This remains a complete mystery. No, quite the opposite. Quite the opposite. No, quite the opposite. I mean the following. I mean, you can have a piece of viscoelastic polymer melt, for example, whose tau is 100 seconds. Okay, 100 seconds. Whose 100 seconds? Whose tau is 100 seconds. Is 100 seconds. Whose viscosity is, of course, huge. Such a material with 100 second tau, you have no trouble going with your time resolution. You just deform that for the first second or so, which you can easily record. You find the response, the stress to your deformation. It's just negligibly small. Of course, it lovely obeys this law. In fact, by the way, this is another mystery. It's beyond my lifetime to solve. The Maxwell model accurately captures the essence of this. I try to tease my student all the time about Maxwell model because one layer is a liquid, one layer is a solid. I keep asking, when you start, does the liquid layer shears or the solid layer shears? It turns out the liquid layer stays and solid layer shears. For reasons I developed in previously, but you can intrigue yourself with. As I speak, however, I remain puzzled. I'm aware of it, that I have a shear rate applied to it. I also know this material has a high viscosity and has high relaxation time. And I have no problem with resolving this relaxation time now. In fact, the problem is exactly the opposite. You can only get the viscosity of this material if you start to make a measurement on time scale longer than tau. But not at the beginning. I think our discussion, which is I love it, it becomes somewhat circular. I see the logic becoming. No, indeed. No, indeed. I'm talking about at the beginning, where the deformation is quite small. And then it turns out it fits the idea, but because the deformation is small, therefore the stress is small, which is what Hooking's law tells you. I'm unsure I could find a way to comprehend the idea why my material does not resist to the deformation in a viscous way. Or in a, I'm running out of words. What?
So you're saying, why doesn't it automatically start as a viscous response?
Yes.
Does it show this Hookean initial response?
Yes. Maxwell model automatically says it does not flow. Okay? I just believe, you can solve it, and I tried it in my. I also understand why there is no flow in the idea of treating this network as a, due to uncrossability, it's initially locked in. It's not diffusing around. So I'm treating a piece of rubber. I guess the cheaper question is this. You cross-link your polymer. Now, in our classical treatment, of course, we say, oh, there's a rubber elastic response. The question is why the viscous part is just imperceptibly small. You got a shear rate, yet it's not generating any viscous response. I know I'm telling you the answer, which should already alarm you. When I say alarm you, I mean that I'm making the joke that all the terminology in the literature called viscoelasticity from today on should all be called elastoviscous. I'm making a joke. I'm saying the response is always first elastic, then viscous. We shouldn't call our thing viscoelastic, we should call our thing elastic viscous to remind ourselves what we have always been dealing with. I think you are too quick to accept the facts. Yeah, these are the facts. These are the facts, and this tells me that colleague of mine, that professor, is wrong when he answers to me that, of course, there's flow as soon as you start the deformation. And therefore, I indicated there are thousands of typos in the literature. They are quote-unquote typos. They call this startup, they don't call this startup, they call it startup flow. And that's not a typo. That perhaps is a misunderstanding of what you're dealing with. So I have always, in the book or anywhere else, tried to avoid calling it startup flow. You can just call it startup shear. You can call it startup deformation, but don't call it flow because there is no flow in the beginning. I think we have to stop here, but there is more to that meet your eyes in the future on this. But this is a good point to call quit. I think maybe throughout this course we'll find the answer. No, I'm not even joking but I'm throwing this question to you about why. Any questions further? Okay, let's